Hi students. Video 6.3, we're cranking these out today. Definitions now for designed experiments. Hopefully you just watched the steroid example. I'm going to link all of these definitions back to the steroids. I've got them on the sideboard, but you have this in your notes. So if I point to something you can't see on the screen, refer back one page in your course packet. All right. We've done an example where we've really talked about all of this. Random assignment. When you're doing a design experiment, you need to have random assignment. The process in which an experiment, when it's randomly decided which treatments get to go to which experimental units. In the steroid example, we use something as simple as we just flip coins. Right? We flipped coins to determine. And I guess there were four groups you could get in, right? There was the, well, I could say here, there's the steroids, and there was HGH, human growth hormone, and we flipped coins to determine which of these four groups that you ended up. Maybe you got both drugs, only steroids, only HGH, and then one group had neither drug, so N and N. And we flipped coins first to determine if you were in steroids or not, and then once you were in that group, we flipped coins to determine if you got HGH. Okay? You don't have to use coins. You can use a computer, random number generator, pick names out of a hat, etc. to pick groups. Okay? But you need to do this. If you don't do a randomization, then people reading your results may not trust in the results. They might think something's biased. So make sure that you've got a random assignment. All right, oh, perfect. I don't even have to erase this. What the heck's a factor? A factor is a variable with values that are controlled by the person running the experiment. Factors are randomly assigned. So, steroids example, we have two factors. Right, these are our two factors. One factor was steroids, the other factor was HGH. Okay? These are the things that as a researcher or statistician that I am manipulating. Okay, those are factors. A special kind of factor, and I'm calling it a blocking factor. I'm not sure if that's putting that word factor there as in every textbook, but we'll call it a blocking factor. This is a variable, again, it's controlled by the person running the experiment, but it's not randomly assigned. If you remember in the steroid example, we had that blocking factor, and that was which league do you play in? Do you play in the American League, or do you play in the National League? AL for American League, and L for National League. Okay? Not all experiments have a blocking factor. You can have no blocking factor, one, multiple, but we thought this through, and we thought that American League might have more power hitters compared to the National League. I don't want the flip of the coin to put all my American League players in the steroid group or the steroid HGH treatment. So I make sure I have equal representation. That's called a blocking factor. It should take that out of the equation, and that way I can determine it's not league that's causing you to hit more home runs. It's actually steroids or HGH or some combination. Okay, so blocking factors, not random, but may affect the outcome of the experiment. Flipping to the next one, let's see here. Yep, level. Level and factor is a little bit tricky. Students confuse this at times. The level are the specific values that the experimenter chooses for the factors. So for the steroids, there's two levels. For the steroids, one level is yes, you get steroids. And the second level is, no, you don't get steroids. The factor is steroids, and these are the two possibilities, yes or no. Same thing for HGH. That's a factor with two levels. Either yes, you get HGH, or no, you don't. You can even look at the blocking factor league and say, yes, there's two levels for that one as well. American League versus National League. All right, so these are the levels. Right, make sure we do get those straight because they are different. Finally, all this terminology, what the heck's a treatment? The exact combination of the factors and the levels that are applied to each experimental unit or person. Here's your treatment, right? One treatment was the baseball players that got both steroids and HGH. Here's a second treatment. Here's a third, and here's a fourth. So we had two primary factors with 2 levels each. 2 times 2 makes 4, and there are 4 possibilities for a treatment. I want to keep the blocking factor out of the treatment. I realize the way that we set this up, we were striving to have half of my players to be American League in the yes group, half the players to be National League. Because that's not random, let's keep that off to the side as a blocking factor. And these are the treatments because this is what we are randomly assigning to the baseball players. Okay, so 4 treatments, 1, 2, 3, and 4. All right. Moving forward, I guess, response variable. Whenever you run an experiment, you have to measure something at the end of it. For the steroid example, what did we measure? Let me make some space here. Response variable, the variable whose values are compared across different treatments. This is the observed outcome of each trial. At the end of the season, what are we measuring for each player? It's number of home runs. Now, we did have 50 players for each of our treatment groups. Of course, we would summarize those 50. We would take all those response outcomes and summarize that, typically with a mean. But you have to measure something at the end of your experiment, and clearly this is number of home runs. If you think back to the math example, when we did the revamp of developmental math, I guess the response variable would be, like, for each class, what's the pass rates? Or if we looked at students in aggregate, you could say, did they pass or didn't they? Right? And based on that. Or you could look at final grades for the students. Again, after the developmental math one, you'd have to measure something at the end of the experiment. Probably the easiest definition here, moving on, experimental units. Individuals or objects on which the experiment is performed. To be nice, if it's people, we'll usually call them subjects rather than calling people an experimental unit. So easy, we can't get this one wrong. Clearly it's the 200 baseball players. 200 Major League Baseball players. What am I performing my experiment on? That's the experimental unit. And here, that's a pretty easy one. Okay, control group. Probably heard this before. Let's formalize it, make sure we know what we're talking about. Experimental units assigned to maybe a baseline treatment, or a placebo, or even no treatment at all. In our steroid example, it's obvious, right? The baseline treatment, these were the 50 players receiving what? These are the 50 players that were receiving nothing. Nothing is the baseline treatment. No HGH, no steroids, right? This word here may or may not know what a placebo is. I'll define it here on the slide, but a placebo is sort of like a fake treatment. Perhaps you have anxiety. There was a famous study where people with anxiety were given a fake Xanax pill, and the fake Xanax pill did just as good in clinical trials as the real Xanax pill. People with cold and flu symptoms have been given sugar pills, and the sugar pill did wonders. People who take a sugar pill think they're getting a medicine. It makes them feel better. Okay? I think on one of the videos we watched from a TED Talk, there was another study that said people who receive 2 sugar pills actually feel better than people that receive 1 sugar pill. These are all placebos, okay? Possibly in the Major League Baseball example are steroids. All I can remember is from Barry Bonds, the steroids was coming in the cream and the clear, and I believe this was a rub. You rubbed it into your skin. Possibly for Major League Baseball, we could have the steroid cream. I don't know if these are steroids are given with needles anymore, or if it's just a cream. And possibly we'll fake the players out. The other ones, we'll give them moisturizer. Of course, we'll put it in the same container, and so players won't know if they're getting steroids. So the players on steroids will get the cream, and the players who were randomly put into the no steroid group will get moisturizer. This would be a placebo, right? They think they're getting steroids. If you think you're getting steroids, maybe that makes you hit more home runs. Maybe you feel stronger inside, even though you're just rubbing some Jergens or something on your shoulder every morning. Next one, and students, I think, yep, statistically significant. This is super important. I'll even label it as such here. Make some space. You've got a whole page to write, and we might need the whole page. Let's try to get this. When the observed difference at the end of an experiment is too large to attribute to chance, we consider the difference to be statistically significant. I'll say it again because it's important. When the observed difference at the end of an experiment is too large to attribute to chance, that would be called statistically significant. Remember how we put players into their treatment groups? We flipped coins. Just because I flipped coins, can I presume that the average home runs will be precisely the same in all 4 treatment groups? I can't, right? So let's get some things down here. We'll call this scenario 1 and scenario 2. Scenario 1. All right, how can I stay organized here? Let's see. So we'll just write this out longhand. The mean, I've got 4 groups, right? Scenario 1, here's the mean. First group was on roids and also on HGH. And we never ran this experiment, so what I'm going to do is I'm just going to make up some numbers in just a minute here. Okay, so I've got the first mean for the first treatment group. Here's the second mean. I wrote mean out. I could have used the symbol Y bar. Hopefully we didn't forget that, right? The second group, yes, they got roids, but no HGH. And there's 2 more. We'll get them down. So here's the third mean. Yes, whoops. Now we're on no roids. But yes, they did get HGH. Last but not least, the baseline. No and no. So we've got a mean here. There were no roids and no HGH. Statistically significant. If the observed difference at the end of an experiment is too large to attribute to chance, we would say that it's statistically significant. This does not go away. The rest of the course, this idea is with us. So let me put some numbers. Pretend this happens, scenario 1. The mean for the double yes group happened to be 19.4 home runs. Those were 50 players, and here was their average home runs. Okay. The second group, yes to roids, no to HGH. This group, 18.9 home runs. I'm making this up. I don't want anybody to think that these numbers came from somewhere. Making it up on the fly. Third group, no roids, but yes HGH. Let's see. Maybe 19.2 home runs. And finally, the clean group, no roids, no HGH. Let's say they had, 19.1 home runs. Which group did the best? Well, the highest number of home runs was the mean here. We had yes to roids, yes to HGH. So 19.4. Common sense, but bringing it back statistically as well. Do these differences seem to be statistically significant? Do those differences seem to be too large to attribute to chance? The answer is no, right? Could the coin flip resulted in results like this? I think yes, the coin flip could have resulted with home run totals like this when we averaged them out. By the flip of the coin, I could have just happened to get two of the best power hitters in my roids group and HGH up top. It wasn't the roids or the HGH, it just the flip of the coin put 19.4 average home runs up here. The flip of the coin put 18.9. Do these means convince you that the roids and HGH is the best? Now, we're not running any formal statistical tests here. We would have to know a lot more information, and actually probably in our Stat 2 class we could make the determination. But this does not feel statistically significant, right? Scenario 1 does not feel statistically significant. Those home run averages seem to be too close together that one of the treatment groups was superior to another, or one was the worst. They're all very close. Now, when we start to tie things together, you're probably thinking, I would need to know a lot more information, like what's the standard deviation for each group? Are these far apart when it comes to the standard deviations, right? And this compared to each of them. At this point in the course, that's a little bit beyond where we're going to get. The point is that those do not feel statistically significant. Those results could have happened because we flipped coins, and roids and HGH have nothing to do with home run totals. All right. Scenario 2, obviously, we'll change this up and show you what statistically significant looks like. Scenario 2. Get this out of here. I'm not going to rewrite these, so if you need to pause the video for a second, if you want to write it down a second time, I am going to get rid of this and keep this because I don't feel like rewriting it, but you've got pause on YouTube. Scenario 2, this is going to be the yes statistically significant. At least it's going to feel that way. Yes, statistically significant. End of the season, 50 players in each group. The roids and HGH group averaged 29.4 home runs. Let's make this out of the park statistically significant. No pun intended. Let's say the mean for the yes roids but no HGH group was, we'll call that, let's do a 28.9 home runs. And the mean for the no roids, yes, we're just going to put this way down here at 17.1 home runs, and the clean group we'll put at 17.7. I'm making this up. I'm doing the what if game. Scenario 2. Statistically significant, when the observed difference at the end of an experiment is too large to attribute to chance. Do you think the flip of the coin was responsible for 29.4 and 28.9 in my roids groups, whereas we're down in the 17s for my no roids groups? It's just so unfeasible. It's so unlikely that the flip of the coin could have put all the best power hitters into the roids group. Now, could it have happened? It could have happened. Is it likely to happen? No way. These are so far ahead. I mean, this is almost what? This is about 12 home runs, roughly, more than the non-roids group. This is about 12 or 11 home runs, more than the non-roids group. These differences are so big, and I did this on purpose to just say it's the two roids groups that are way above and the two non-roids groups that are way below. But those differences do seem statistically significant. As you move on in statistics, you start to run formal tests. Here we're doing an eyeball test. We're saying it feels statistically significant. Now, that doesn't cut it once you move forward, but for this video, to get the baseline idea, definitely feels statistically significant. The problem becomes, what happens what if this was 19.2, and what if the roids and HGH was, say, 20.3? You're getting in the gray area, right? Definitely the roids groups are higher. This is bad English, but are they higher enough? Are they far apart enough to convince me that it was the roids? This is where we're going in the course. We're going to start running formal tests to determine if this happened, the 20.3, the 19.2, is that statistically significant? Okay, I'm nearly certain that's the end of the definitions. It is. Think about this. It's a difficult concept, but it's going to come up again and again. So ask questions if you don't understand, and thanks for watching.